All right. While you all are logging in and whatnot to Blackboard, we'll go ahead and get started. Let me go through a few quick announcements before we get into things. So first off, I mentioned this last time, but if you recall, we're not going to have class on January the 26th because that's the date of the annual technical conference that we host here on campus. There's a lot of folks there that attend that conference to get their continuing education, which means there's a lot of practicing engineers there and a lot of folks that are looking for interns, nudge, nudge, wink, wink. So a couple things. First off, since you all are freshmen, you might be new to this, but because we have a lot of practicing engineers and a lot of folks from places like the DOH and the Army Corps and a lot of consulting firms and whatnot in attendance, there's the attendees all sit at these round tables, and on each round table is a resume booklet. And what we do is anybody that's interested that's in having their resume placed in this booklet, we print them all off, and while the attendees are listening to the presentations, they'll leaf through resumes and go, hey, maybe I want to hire them to be an intern for me this summer. So if you're interested in having your resume included in that booklet, you need to send it to Noah Morgan. It's morgan268@marshall.edu, and send that by the 17th, and what they'll do is they'll print it and it'll be on every table there at the conference. So maybe not the worst idea. Also, we're not having class that day. So one thing you might want to consider is being a volunteer that day, and there's all sorts of things that need to be done. You know, helping set up the tables, helping people find their parking spot and find their way to the conference. That's a great way to rub elbows with somebody who might be hiring you. Next thing you know, you're just walking down the hall with an attendee. They ask you your name, ask you what your plans are for the summer. They give you a business card. Funny thing, you might call the number on that business card and have an internship over the summer. So if you're interested in being a volunteer, I'd contact Logan Stacks. His email address is stacksl@marshall.edu as soon as possible. I mean, most of the work that's done in preparation of the conference is before the conference, so it's early in the morning. And since you're not having class that day, I know you're free. So if you're interested, contact him. Well, it's true. Well, if you're interested, contact him as soon as possible. Definitely the more the merrier. Another heads up, I'm probably going to have some classroom visits throughout the semester. Some various professors across campus will be coming visiting the class. So if at some point you see some random chemistry professor or some visual arts professor just sit in, don't freak out that they're supposed to be here. Although in this class we're pretty jam-packed, so I don't know that we're going to have that many visitors, but I just thought I'd give you a heads up. Last, homework 1 is assigned today. It's just on some of the fundamental stuff we're going to talk about today and talk about on Tuesday. It's not due till next Thursday, and it's not a terrible amount of work. I think you'll probably finish it very quickly. Everything on Blackboard should have turned on, like right now. It was supposed to activate at 8 a.m. I know you had asked. Is it up yet? Okay. All right. Any questions before we get started? All right. So today, what we're going to talk about is some pretty basic stuff, things like orders of magnitude, significant figures, units. Dependent upon your background, this might be new material or this might be stuff you've heard before. But I think it's good to cover this at the very beginning just so everybody's on the same page. You know, the last thing that we would want to do is assume that you know this stuff and then we find, well, you hadn't been exposed to it before. So it's a good idea to, I think, go through this at the very beginning. So I'm going to go ahead and go through the notes. The notes should have appeared on Blackboard as well. So you're more than welcome to pull those up and go through them with me. That's fine. So we're going to talk about a few things, prefixes, orders of magnitude. Let's just go ahead and get into it. So the first thing I want to mention are some things regarding engineering prefixes. I imagine even if you've never had a physics class or a chemistry class, you've seen some of this stuff before. You know, prefixes like kilo and mega and giga. I mean, even just looking at your knowledge of computers, you know, this file is so many megabytes, this file is so many gigabytes, this file is so many kilobytes. I'm sure you all have heard those types of those prefixes before. They're primarily used a lot with SI units, things like kilograms, things like centimeters, and what have you. This is stuff that you're going to be exposed to throughout your engineering career. So you'll probably want to retain some familiarity. Now, I'm going to be honest with you. I'm not going to expect you to remember, femtometers or adiometers or whatnot. I'm not even sure that I remember those. But the ones that are in the middle, giga, kilo, milli, micro, things like that, those are the ones that you'll definitely want to have a handle on. So this is this here is just sort of a general, a big table. The next two slides are just to be a little easier on your eyes. So these are the upper scale prefixes, the things that are larger than 1, so deca, hecto, kilo, mega, giga, et cetera. Everything up to tera is pretty much what you would need to know. We're not going to expect you to remember, peta or exa or anything past that. So as long as you're good up until tera, you're good. You're fine. These are the lower scale prefixes. Anything up to pico, you should be good. So think, if we're talking about meters, so decimeters, centimeters, millimeters, micrometers, nanometers, and picometers, that would be what you'd kind of need to remember. And they go down. So decimeters would be like 0.1 meters. Centimeters would be 0.01 meters, et cetera, et cetera. Is everybody okay with this? I have a feeling have you been exposed to this before? Oh, okay. All right. That's good. Again, if you've got any questions or there's something new, don't hesitate. Don't hesitate at all to ask. Please, that's what we're here for. So if you've got any questions, I want to address them as best as I can. Sound good? All right. Like I said, pretty basic stuff. Okay. This one might be a little new, but this is just sort of a rule of thumb, an easy way that we engineers can test whether or not a computation that we have done is correct. And that's using orders of magnitude. And an order of magnitude is really just a fancy way of saying, on average, what should our computation result in? For instance, if I did an estimate of the number of people in this room, it shouldn't be in the thousands, right? It shouldn't be in the hundreds. It should, at the very least, be in the tens. We're talking about 30-some people in the room, so it should be in the tens place. Does that make sense? That can help. That's a pretty easy example, but later on, you're going to be exposed to some equations and some computational methods that are pretty long. They may not be difficult. They're just long. For instance, I'm thinking of some equations that we use in steel design to compute various buckling lengths. And they're not difficult equations. They're just really long. They're about yay long. So you take all these values and you're plugging them in to a calculator. It's very easy to forget to put a decimal point in or put it in the wrong spot. And suddenly you've got this massive equation. You're not 100% sure whether or not it's right. But if you have a general understanding of the theory, you should know that that equation should give you an answer, maybe something like 15 feet or 16 feet. And then if you get 246 feet, you know you did something wrong. You see what I mean? So this is sort of a general idea, just to ensure that while you're performing a calculation, that you're on the right order of magnitude. So just some pretty basic stuff. So orders of magnitude are on a factor of 10. So, 10 would be one order of magnitude larger than 1. 1,000 would be one order of magnitude larger than 100. 1,000 is 2 orders of 1,000 is 2 orders of magnitude greater than, et cetera. Does that concept kind of make sense? Let me give you an idea as to why this works. Like I said, they're rough estimates, but they can at least give you sort of a general idea as to whether or not your computation is correct. Let me skip ahead to a real life example to give you kind of an understanding of the value of this. So this is a pretty easy calculation, but I want to go through this. So we've got a coal-fired electric generating unit, and it's consuming, we've got here 600 tons of coal per hour. So that's a lot of coal. All right. So if we operated this unit continuously, how many tons of coal would the unit consume in an entire year? Now, are we talking about hundreds of tons, thousands of tons, tens of thousands, what have you? You see what I mean? Now we can do the calculation. It's actually a really easy calculation to do. But the purpose of this example is to try and ensure, is our answer making sense? So what do you think? Are we looking at, thousands? Are we looking at millions? What do you think? Just offhand. Anybody? Millions. Okay, so somebody's got millions. Let's see if that works out. Now, before we jump ahead, and you all can jump ahead if you want, but I want to get you a little bit engaged. How would we go about doing this calculation? So we've got 600 tons of coal per hour. How would we determine how many tons of coal we would consume in a given year? Let's make it simpler. If we got this many tons of coal per hour, how would we determine how many tons of coal we produce or we consume in a day? Multiply it by 24, right? So that would tell us how many tons of coal we produce in a given day. What would we then multiply that to determine tons per year? 365, all right? Okay, sound good? Or 366 if we're in leap year. So, all right, sound good? All right, so I want you all to understand, this is a calculation that we can do pretty readily. So if I take 600 tons of coal per hour and then multiply that by the fact that there's 24 hours in a day, and then again multiply that by the fact that there's 365 days in a year, I can go through and do the math. And the math will tell me that that's about 5 million tons per year. Or if I wanted to write that in scientific notation, 5.25 times 10 to the 6. So is everybody okay with this? The idea of taking a number and then converting it to scientific notation? Everybody okay with that? Okay, so you were right. We're talking about millions, okay? But let's say for some reason you forgot your calculator, which an engineer forgetting their calculator, goodness, that's like cardinal rule number 1. Can't forget. I mean, you're an engineer. Goodness. I'm going to get some snickers and laughs out of you. I know it's 8 o'clock in the morning, but it's going to happen. So just bear with me. All right? An order of magnitude estimate is a way of determining whether or not your answer makes sense. And here's the long and short of it. What we would do is take each of those inputs and round them to the nearest order of magnitude. So for instance, if I'm talking about 24 hours a day, I'm not talking about hundreds of hours or thousands of hours. I'm talking about tens of hours. Does that make sense? So I'm rounding this to, 10 or 10 to the first power. So if I'm talking about 365 days in a year, I'm talking about hundreds of days, not thousands of days or millions of days. Make sense? If I'm talking about 600 tons an hour, round that up, and I'd round that up to 1,000. So we're talking about thousands, not millions. All right, make sense? So if I take 10 to the third times 10 to the first times 10 to the second, y'all remember that if you've got a bunch of numbers that are multiplied and you've got exponents, all you have to do is add them up? Y'all remember that? So 10 to the third times 10 to the first times 10 to the second is just 10 to the 3 plus 1 plus 2, so it's 10 to the 6. So the actual, correct answer is in the millions, and that's what our order of magnitude estimate yielded. Make sense? So that's something we can do in our heads. We don't need a calculator to do that. We can just, rough that out and make sure that our answer is, in fact, matching our response. Sound good? I just realized I forgot to pass the attendance around. Oops. I forget that from time to time. All right. So far, so good? Now, if we wanted, we could sort of step our game up a little bit with the order of magnitude estimate, and instead of rounding to, the tenths or the hundreds or the thousands or something like that, we could round to one significant figure. And we're going to talk a little bit here in a second about what that exactly means. But essentially rounding to one unique value. So, 24 hours a day, I might round that down to just 20. If I've got 365, I might round that up to 400 to just have that one unique value. 600, we'll just leave that as it is since it's not really rounded. This is stretching it a little bit. We can probably do this calculation in our head as well. 600 times 20 times 4, well, 6 times 2 is 12, 12 times 4 is 48, so we know we're going to have like a 48 as a prefix to that value. Does that make sense? And again, this is also another verification of our calculation, because that's pretty close to the final answer as well. Now again, this is a pretty simple example, but I mean later on, we engineers sometimes use some pretty long equations. So having just a general understanding, if the calculation or the computation produces a result that's reasonable, that's pretty important for what we do. All right. Everybody with me so far? Okay. All right. So I've got here this idea of significant figures. I need to probably do a little bit of diligence and talk about that as well. So significant figures, essentially, their purpose is so that when you're conveying some answer, that you're conveying it to a degree of accuracy that you can depend upon. For instance, here's a random one. How tall do you think I am? Anybody? It doesn't matter. 5'11". Okay, we got 5'11". We got 6 foot. 7'2". Okay. I guess that's a compliment. But notice what everybody's saying. Okay, we got 5'11", we got 6, we got 7'2". But what are you expressing your answers to? To the nearest what? Nearest inch. Nobody said I'm 6 foot 1.268473962 inches tall, right? Nobody said that. They said to the nearest inch, right? Because if you're making a guess, even if it is an estimate, you're only guessing based on a value you can depend upon. And there's something, I think, in the back of your head that kind of goes along with that. I mean, when I asked you how tall it was, you only said to the nearest inch. Nobody started spitting out decimals, right? Make sense? Well, when we do computations, we've got to follow that logic around as well. You know, if you take if we're doing something like a structural analysis, I do a lot of references to structural engineering and bridges and things like that because that's what I do. So if you're an electrical engineer, I'm sorry, I know that when you hit this button, the lights come on. That's about my extent of my knowledge of electrical engineering. That's being a little facetious, but it's actually not that far off. But if I do an analysis, and I'll try and frame it in a somewhat realistic setting. If I do an analysis, let's say of a roof truss or a bridge or something like that, I'm trying to determine the amount of forces that are in those elements so that I can then design them. You know, how big does this beam need to be? How deep does this column need to be, et cetera. So in my world, in the world of structural engineering, I mean, I'm dealing with forces that are quite large. I mean, it's not that uncommon for me to design a column for something like 500,000 pounds. That's not that uncommon, you know. But very rarely are you going to see me say, well, I need to design that column for 500,286.3469247 pounds. It's not going to affect anything, okay? But here's the thing. When I go through and take the values and plug them into my calculator and press equals, the calculator, it doesn't know that, okay? I'm taking these values and plugging them in, and it's reporting 500,286 point da-da-da-da-da. So I have to use a little bit of judgment and a little bit of relative certainty to express those values in a usable fashion, okay? Now, there's a few rules that we adopt to go along with significant figures, so I wanted to go through some of this. So, for instance, we're going to refer a little bit to leading zeros and trailing zeros. So just to kind of express that, I've got some decimal value here. Any value, like if I've got 0.00 something, all of those initial zeros are what are called leading zeros. And they're not significant because I could then take this number and express it in scientific notation, and I wouldn't need those. They wouldn't be necessary. To express this particular value in scientific notation, I would start at the 3, and I'd say 3.5624 times 10 to the, whatever. So these values are not really necessary. The trailing zeros, however, they are significant because what they're indicating is that when I took this measurement or when I performed that computation, I indicated those trailing zeros because they, in fact, mattered when I took the measurement. So any leading zeros aren't really going to matter, but trailing zeros are significant. So when I look at this particular value, whether or not I look at this expression of the value or this one, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 11 significant digits, okay? Both on this instance and this instance down here. Does that make sense? Be okay with that? Okay. All right. So a couple things. So any value that is not 0 is obviously significant. So if I'm looking at numbers like 175, 25.5, if I've got something like 1.85 or 0.0125, all those values have 3 significant digits. Remember, the leading zeros don't matter. One of the nice things about scientific notation is it does tend to remove a little bit of the ambiguity associated with significant digits. Because, for instance, if I just say 1100, how many significant digits are in 1100? Well, it could be 2, it could be 4. It actually could be 3. You know, there's no decimal place listed, so I don't know if those 2 zeros here at the end are significant or not. Any trailing 0 after the decimal place matters, but if there's no decimal point, I don't know that it matters, or I don't know. Writing it in significant notation clears up any of that ambiguity. For instance, if I write 1.1 times 10 to the third, numerically this value equals 1100, but this is a much more appropriate representation for a value like this because I know in this format there's only 2 significant digits. Make sense? So it's one of those things where if you're trying to express the value and you're trying to express it to a given precision, scientific notation is a way of sort of removing any of the ambiguity out of the issue. By expressing it in scientific notation, you're always going to know the correct number of significant digits. The nice thing about this calculator is that you can easily just hit the button and there, your value is always in significant digits. So you don't even have to do much, judgment in regards to taking a number and converting it. You can just sort of put the blinders on and items like this will do it for you. Same thing with things like Excel and whatnot. You can always format numbers to spit out in scientific notation, and then you can just go accordingly. Sound good? Okay. All right. So here's some basic rules for rounding. I mean, if you do a computation and you get 3.6974243, so on and so forth, and you need to express that in 4 significant digits or 3 significant digits, you need to do some rounding. Okay. So here's some basic rules for rounding. So for all of these examples, we're going to round to the tenths place. If we were rounding to the hundredths place or the thousandths place, it'd all be the same. I just wanted to do something that was pretty basic. So if your hundredths digit is 0, 1, 2, 3, or 4, you would round down. So anything under 5, you would round down. So for instance, this is 5.23. If I was rounding to the tenths place, this 3 would indicate I'd go down to 5.2. If this was something like here on the bottom, like if it's 6, 7, 8, or 9, I'd round up. So this value would round up to 45.7. Everybody okay with that? Now, if the value is in fact 5, what we do usually is we sort of split the difference. So if this digit is odd, we would round up, and if this digit is even, we'd round down. So for 33.75, do we do 33.7 or 33.8? Well, this is odd, so we round up. This one's even, so we round down. The idea is that throughout all of your computations, if you're rounding half of them up and half of them down, you're sort of breaking even at the end. Does that make sense? Everybody good? Okay. All right. Now, when you're actually doing computations, a couple rules. So, when you're adding or subtracting, okay, when you add or subtract, you record based on the last common digit. So the idea is, if I look at this computation here on the left, so I do 164.57 plus 4.3, and you all could break out your calculators now or your apps on your phone or Excel or what have you. You plug these numbers into a device, and the device will spit out 168.87. That's what it will actually spit out. Now, this value was accurate to the hundredths place. This value was only accurate to the tenths place. So this is what the calculator is reporting, but what I need to record is, what can I hang my hat on? Can I rely on accuracy to the hundredths place, or can I only rely on accuracy to the tenths place? Make sense? So I'm only relying based on that least digit, so my recorded answer would be 168.9. Again, taking this, rounding up, and saying that's all I can hang my hat on. Does that make sense? Okay. Likewise over here. Same thing with subtraction. So if I have 113.259, what have you, and I just say minus 4, okay, the calculator's going to read 109.259. This one's accurate all the way to the thousandths place, but this was only correct to the ones place. So I can only hang my hat on 109. Sound good? All right. Now that's addition and subtraction. Okay. Multiplication and division, it's a little different. For multiplication and division, all we do is we record based on the least number of significant figures. Okay. So for instance, if I look over here on the left, so 25.34, that has 4 significant figures, right, as it's written. 7.3, that has 2 significant figures, right? So if I open my calculator right now and I do that math, it's going to spit out 184.982, okay? So that has what? That has 6 significant figures, right? But I can't hang my hat on that, right? This has 4, this has 2, so I always go to the lowest number of significant figures. Now let me ask you this. What would this number be rounded to 2 significant figures? Like just think about this. If I was rounding this to 2 significant figures, what would I round it to? 180. Okay? The problem with that, though, is it goes back to what we were saying earlier about this. If I just write down the number 180, that last 0, is it significant or not? Well, it's a little ambiguous if you don't use scientific notation. But if I say, well, this is 180, right? This is 180, but I've also removed the ambiguity because now I know by saying 1.8 times 10 to the 2, I know I only have 2 significant digits. Does that make sense? Sound good? Likewise, over here on the right, this computation, this will yield a calculation that'll go on forever because, you know, I've got 142.611. That's a typo. That should be 6 significant figures. Divided by 42.3 with 3, go through and do all that. The decimal will go on forever. But again, going off the value with the lowest number of significant figures, it should be 3.37. Sound good? All right. Sorry about that. That's a typo. That should be 6. So, whoops. All right. I'm allowed to make, I think the rule is I can only make 7 mistakes in a given semester. Is that what it is? 7. So that's 1. But considering how I'm the one that keeps count, it's a little rigged, isn't it? All right. The joke will develop as the semester goes. Okay. All right. One other big point I do want to talk about in this course is units. Okay. So when we perform a calculation, more often than not, there's a unit associated with it. How tall did we say I was? Somebody said what, 7'2" or 6'1", but what does that mean? 6'1". What does 6'1" mean? 6 feet and 1 inch, right? So 6'1" doesn't really have much significance, but 6 feet and 1 inch, now we're talking. Now we're expressing a quantity that has some dimension to it, right? I mean, what is it? 6'1", is it 6 miles and 1 kilometer? Like, I would be really tall, you know? So, so you know, when we perform a computation, we have to express a unit that goes along with it. And I'd say, by and large, units are an issue that will affect you throughout your engineering career. I mean, right now I'm teaching freshman course, this one, and I'm teaching senior level courses. And I've taught everything in between, sophomore, junior level, graduate level. And I'm telling you, units is something that always tends to pop up and cause people issues. You know, they forgot to convert feet to inches and their beam deflection's off or something. It always happens, but it's always something you want to make sure that you're being cognizant of. So, you know, for instance, if we're performing a calculation, you know, even if we take care of significant digits, you know, 123 doesn't mean a whole lot. 123 feet does. 3,500 doesn't mean a whole lot. 3,500 pounds per square foot, PSF, that matters. 43,560 square feet in an acre. Like that makes a little more sense. Sound good? All right, so we're going to talk a little bit about this. One important aspect of units, and this is something that I don't think students take advantage of sometimes, is that not only is expressing the appropriate unit important, but in a way, they can help you verify whether or not your answer is correct. You know, if you do a calculation, and let's say you're calculating a pressure, okay? Well, that pressure, I mean, I've got here a different example on the screen, but let's just keep it simple. What's a common unit for pressure? PSI, right? Anybody who's driven a car or ridden a bicycle knows that, right? PSI, pounds per square inch. What if you went through and did the calculation and it came out as pounds per inch, or pounds per cubic inch, or if it just came out as pounds? Something's wrong, right? So if you know that you're calculating a pressure and you know you should be getting PSI and you're not, you did something wrong. And it can serve to check whether or not what you're doing is correct. Let me give you a realistic example. So this is a little up my alley. So I'm a structural engineer, and I teach things like steel design and concrete design and structural analysis. This is a very common problem that you will have in one of my classes later on down the line. So I have a beam, you know, it's got some length to it and whatnot, and I'm placing a load right in the middle. Now, one of the rules of deformable bodies is you take an element, you put a load on it, it bends, right? It deforms, okay? So if I have a beam and I apply a load to it, it will respond by deflecting some amount. So we call this distance delta, you know, how much it deflected down. Make sense? That's what this triangle is. We're talking about delta. Now, we're not deriving the equation in this class. We'll do that much later, you know, down the line when you take mechanics of materials or structural analysis or things like that. So for now, I just want you to take the equation I have up here on face value. But based on this situation, if you want to determine how much that beam deflected in the middle, the equation that you would use is PL cubed over 48 EI. Now, let me explain what each of those mean. So P is the applied load. Are you putting 20 pounds on the beam, 200 pounds, 360, what have you? However many pounds you're putting on the beam at midspan, that's P. Okay, now I'm using U.S. units. I'm saying, you know, pounds and feet and things like that. This will also work if we're using SI, you know, newtons and meters and what have you. All right, so that's what P is. L is the length, how long the beam is. Okay, so it could be 4 feet, 20 feet, whatever. All right. E is a term that's called the elastic modulus. E is related to the material. So steel has a different elastic modulus than aluminum or copper or concrete or something like that. That's a material property. And I is what's called the moment of inertia. I is related to how strong a beam is under a given direction. For instance, if you're building a porch, you know, on the rear end of your house and you've got, you know, this, you know, extended deck, you're probably going to take all your supporting beams and stick them up like this. You're not going to put them like that, right? Because if you've got, let's say, a 2x4, it's stronger this way than it is that way, right? The reason why is because that 2x4 has a larger moment of inertia in this direction versus it does in this direction. You'll learn about that later on. But the point I'm making is these are all the terms and the units that go into this. But watch what happens when you plug and chug. So if I look here at this equation, I've got PL cubed over 48 EI. I'm not going to worry about the 48 because if I take 2 feet and multiply it by 3, I get 6 feet. So the number doesn't really change what the units are. Make sense? All right. So what do I got? I got PL cubed. So P needs to be in pounds and L needs to be in inches. Like I can't say the beam is 20 feet long. I'd have to say it's 240 inches long, right? So many pounds times so many inches cubed. So on the top, I've got pounds and inches cubed. Make sense? On the bottom, I have this E term, which its units are PSI. That always comes out in PSI. And then moment of inertia, its units are inches to the 4th. I know that's a little bit of a strange unit, but that's just sort of how the math works out in mechanics. Now, if I look on the bottom of this fraction, I've got pounds over square inches, and then I've got inches to the 4th. So what's going to happen? A couple of those inches are going to cancel, right? And on the bottom, I'm going to have pounds times inches squared. So pounds times inches squared on the bottom, pounds times inches cubed on the top. What's going to happen at the very end? The pounds are going to cancel, and I'm going to be left with inches. Sound good? But and doesn't that make sense? I mean, if I've got a beam, I'm asking how much is it deflecting? It's going to deflect, what, 2 inches, 3 inches, or what have you. Make sense? So that's a good idea to ensure what you're doing is correct. Now here's another example. This is just to show that adding units needs to be consistent as well. This is one of the most fundamental equations that you'll ever see in fluid mechanics. You'll also see it in thermo for you mechanical folks. But this is a way that, that we can, let me back up. So this equation is a component of an expression called Bernoulli's equation, and it's used for calculating things like pressure and velocity in fluid conduits, so things like pipes. So the idea is if I've got some piping system and I have some fluid in it, like let's say water, and on one end of the system it's got some pressure, you might be asking, well, what's the velocity over here? Or what's the elevation at this point if this is the pressure over here? And it's a very fundamental equation in fluid mechanics. One thing that's a little strange the first time that you hear it in the world of fluid mechanics is we express energy in a fluid system in terms of distance. In the world of fluid mechanics, we call the total energy the total head in the system. And there's 3 components that contribute energy to a fluid system. One of them is this P over gamma. We call that the pressure head. This V squared over 2G, we call this the velocity head. So this is, how much pressure the fluid is under, how fast it's traveling, and then the elevation, how high or low the head is. To give you kind of a general idea, how many of you all have ever seen a water tower? Right? Well, the idea is the community that the water tower is located in needs a certain pressure supplied to its water system. So the way that we do that is it's a little more involved in this, but the way that we would do this is ultimately determine how much energy we need to provide, X amount of pressure to all the consumers, and then go back and solve, well, how tall does the water need to be in order to provide that elevation, and we build a water tower to reach that elevation. That's the long and short of it. So we measure energy in terms of a distance. So, so many feet of head or so many meters of head. In the end, the units have to work out, though. So, for instance, if I look at this equation, P is pressure, so that's going to be things like PSI, or in SI units, newtons per meter squared. Gamma, this little funky Y-looking thing, that's the Greek letter gamma. That stands for unit weight. So water is going to have a different unit weight than, let's say, mercury or gasoline or something like that. And that's newtons per meter cubed. I'm more of a U.S. unit, so in U.S. that would be, so many pounds per cubic foot. Water, if you had a cubic foot of water, it comes out to about 62 pounds per cubic foot, 62.4 actually. V is velocity, so that's meters per second or something like that. Gravity, that's G, so meters per second squared, and then H is your elevation, so that comes out in meters. But if you notice, all these terms are added together. So when you add them, they need to be of consistent units. So if you go through and do the math, you'll find, newtons per meter squared divided by newtons per meter cubed. The newtons cancel, flip and multiply, and you're just going to be left with meters. Same thing here and same thing here. The second squareds cancel, meters squared over meters comes out to be meters. All right, make sense? You've got to make sure that you've got consistent units going into these computations, because first off, you have to have that anyways, but it can also serve as a check to see whether or not what you're doing is correct. If you're calculating stress in a column and the numbers are coming out really strange, well, look at your inputs. Maybe they don't match. All right, sound good? Okay. Also, I would say utilizing the appropriate unit is important. So if you look at all of these quantities, these are all identical, okay? So for instance, 6,570 days equals 938.6 weeks. That equals 218 months. That equals 18 years. That equals 0.18 centuries. That's all the same. It's like saying 1 foot equals 12 inches. They're both the same quantity, right? Because you've attached a unit to it. But using the appropriate unit with that quantity matters. I mean, if you ask somebody how old they were, would you say they were 938.6 weeks old? It doesn't sound right, right? It doesn't make sense. I mean, nobody's really going to understand that, especially when you're trying to convey your computations to somebody else. You need to use an appropriate unit that makes sense. I mean, if you're asking somebody how old they are, they're going to say something like 18 years. That's how old somebody is, right? Make sense? Even though all these quantities are the same, they're all of dimensional accuracy. It's all about what makes sense, what's appropriate. Now, appropriate units usually depend on the problem. For you civil engineers in the room, this is a unit that you're really going to want to get familiar with. This is something we use throughout all of civil engineering, and that's the kip, okay? A kip it's abbreviated for kilopound. It's just 1,000 pounds. In fact, I've been talking about columns and whatnot, and I've been saying, this column has 500,000 pounds. It sounds even a little weird for me to say that. I never say that. I'd say that column has 500 kips on it. That's just how I think. I don't even think in pounds anymore. I just think in kips. I would say, on average, civil engineers tend to use U.S. units a little bit more than metric. You mechanicals, you're probably going to be a little bit more on the metric side, and I'd say electricals as well. But you electrical folks you tend to also be within your own wheelhouse altogether. I mean, I would never use ohms or amperes or volts in any of my calculations, but I don't know that there are any other ways of expressing current or voltage or resistance or things like that. That's just really what you end up using. So just making sure you're within your correct wheelhouse. I mean, like I say, if you're a civil engineer, you're not going to express that excavation in cubic meters. It's going to be, how many, or that concrete. I mean, usually, what, cubic yards? How many yards of concrete? How many yards of excavation needs to happen? Yeah, it's just what we civils tend to use. One big thing, if you're going to use units, you need to be able to do appropriate conversions, and that involves using conversion factors. Now, we've actually kind of already used conversion factors a little bit today because we said something, when we looked at that coal-fired plant example. We said, well, the coal-fired plant uses, 600 tons a year? We would then take that and we multiplied it by 24. Now, that's true. We took, we went to our calculator, we said 600 times 24, but that's not really the full story. We didn't multiply it by 24. We multiplied it by 24 hours in a day, right? Now, technically, that's sort of like multiplying it by 1 because you're saying 24 hours per day. So 24 hours divided by 1 day. Well, what is 24 hours divided by 1 day? They're equal, right? 24 hours and 1 day are equal quantities. So what is 24 hours divided by 1 day? It's 1, right? So conceptually, you're really multiplying the quantity by 1. Now, in actuality, from a computation standpoint, you're doing 600 times 24. But we do that for a very specific reason. So, for instance, 12 months equals 1 year. Now, 12 doesn't equal 1, but 12 months equals 1 year. Okay? Make sense? Everybody okay with that? Now, you probably ought to memorize some of the more basic ones. I'm not going to lie, there's some very esoteric and out there unit conversions, and that's where, I'm going to be honest, that's where Google and references and things like that come into play. I mean, you shouldn't be expected to memorize every single thing in the world of engineering. I mean, I don't believe that engineering is a memorization science. I don't think that's what it is. It's more about, here's the knowledge, use it. So, for instance, on your first homework assignment, you're going to have some values, and the values are, here's so many, newtons. Tell me how many pounds that is. That's where you go on to Google or open up your physics textbook or something like that and find the unit conversion for newtons to pounds and do the conversion. All right? Make sense? But some of them might not be the worst idea to memorize, like 1 foot equals 12 inches. You ought to know that. All right? Sound good? All right. That's basically all I've got for the presentation. Now, does anybody have any questions at all, just about anything? Life? Anything at all? Yes. What's that? How tall am I? Last time I checked, I was 6'1". So, yes.
So you want the homework formatted on engineering paper, just like the...
Yeah, I want to get to that. I want to get to that here in a second. That's a good point. Actually, let me pull the homework up. Does anybody have any other questions? Yeah.
The sign-in sheet never made it around to this.
It's all his fault. I'm blaming him. I'm kidding. All right, everybody good? All right. Let me pull up the homework. So let me talk a little bit about this. So the homework should be available on MU Online. Does everybody see that? Okay, so this homework, I mean, we're assigning it today, and it's due in a week. But right now it's 8:45, and you all have, like, what, 30 minutes left in class? You could probably finish at least problems 1 through 5 before you have to go to your next classes. They're pretty short quantities, or short problems. But let me talk about that. So the question that he asked was, does this have to be on engineering paper? This assignment does not have to be on engineering paper. If you don't have any, I understand if you want to use notebook paper, that's fine. Just do me a favor. Make sure your handwriting's neat. Make sure you're following the guidelines as best you can. And does anybody have just like a spiral round notebook? Let me see this real quick. Please, none of the perforated edges. Oh, those are the worst. None of those. Other than that, I'm pretty easy to go along with. So
if you tear the spiral part off, you're good to go. But you have to get it so that it's a clean edge.
Yeah, just clean edge. Yeah,
Right.
just clean edge.
So spiral bound paper is not bad as long as it's perforated there. You can pull off
Yeah,
the spiral.
yeah. None of those little fuzzy things at the end. Ugh.
Always bother.
Ugh. None of those. Any other questions? Everybody good? All right. So what I'm going to do is this. I'm actually gonna shut up for a little bit and let you all work on the homework assignment if you'd like. My feelings will not be hurt. I will not have a broken heart if you decide I'm actually going to leave. If this is your only class for the day and you're like, I'll just do this at home, that's fine. But I'm going to hang out for the next half hour. So if you've got any questions, I can work it out with you. Sound good? All right. I'm going to stop the recording as well. So goodbye, YouTube. We'll see you next time.